Hello, my name is Michael Duda, and in this lecture we're going to look at some of the post-processing and visualization options that we at NCAR commonly use when we look at the output from MPAS-Atmosphere simulations. And before we dive in and look at the details of how these post-processing options work, it's firstly important to understand that the MPAS output is on the model's native unstructured mesh, and that's actually true of the input as well. So all of the fields that are either read or written by streams that we talked about in the Running MPAS Part 2 lecture are on the model's native unstructured mesh. And so we can look at an example of a variable resolution mesh here in the upper left of this slide. And if we zoom in, we'll see that many of the cells are hexagons. In fact, most of them are hexagons. But if we look closer, we can see that there are some cells that have 7 sides. For example, this cell right here has 7 neighbors. And there are also some cells in this mesh that have 5 neighbors. And this complicates matters because it means that we can't find, in general, any sort of constant coordinate lines. So in other words, although we have 2 spatial dimensions, it's hard to represent those spatial dimensions in a regular array. And so what happens, in fact, is that all of these 2-dimensional fields, 2-dimensional horizontally varying fields, are written out as just 1-dimensional arrays that list all of the cells in some particular order out to output files. So after you've run an MPAS simulation, you'll get a set of standard output files that are defined in the default streams.atmosphere file. And we're looking at some example file names here in the center of the screen. And as we talked about on the previous slide, all of the fields in these files are on the native unstructured mesh of the model. So what do? Well, one option would be to take these fields on the native unstructured mesh of the model and to interpolate them horizontally onto something like a regular latitude-longitude grid. And once we have those fields on a regular lat-lon grid, we can store that in a rectangular array and manipulate that with many different tools, or visualize it directly using, for example, the NC View tool. The second possibility is to try to render the data in its native representation directly using a language that supports scripting or programming. So this might be something like the NCAR command language, which is being retired, or the Python programming language. And there we have available to us many different graphical packages, for example, matplotlib or Pingle. So in the Running MPAS Part 2 talk, we discussed how we can modify the set of fields that are written to the model output files by manipulating the stream definitions in the streams.atmosphere file. So in principle, you could write out whatever fields you would like, but by default, the model history files contain mostly 3D fields, some of which are listed here. So we get mixing ratios for water vapor, cloud water, rainwater, and a few other microphysical species. We get potential temperature, zonal and meridional winds, and a few others. But the important thing about the history files is that they include not only these time-varying atmospheric fields, but they also include the time-invariant full horizontal and vertical mesh information. And that's a nice property of these history files, because it means that in some sense they're self-contained. They contain not only fields, but the description of the mesh on which those fields are represented. And in some respect, the history files are in contrast to the default model diagnostic files, which don't contain mesh information. These typically contain diagnostics that are created by the diagnostics framework, which we'll talk about in a separate lecture. And these are things like typically 2-dimensional fields, surface fields, vertically integrated quantities, and a few others. But again, the key difference is that these diagnostic files by default don't have mesh information. So when we go about visualizing or post-processing the fields in diagnostic files, we need to pull in the mesh information from either another history file or from the model initial conditions file, which of course also has the mesh information. So with the preceding slides as background, we can talk about the first option for post-processing model output, and that is to interpolate that output onto a regular latitude-longitude grid. And as we said at the outset, because of the unstructured nature of the horizontal mesh in MPAS, 2-dimensional horizontal fields are just represented as lists of elements, in other words, as 1-dimensional arrays. And by extension, 3-dimensional fields are stored as 2-dimensional arrays, where the second array dimension is the vertical or structured dimension. And as I also said, the ordering of the elements in these 1-dimensional arrays isn't something that has to follow any particular order. So what we're looking at here is a very coarse icosahedral mesh with 42 cells. And what we're looking at in this colorful bar here is one possible ordering of the cells in this mesh. But in principle, any other ordering would work just as well, as long as we adjusted the other mesh description fields to match that ordering. And we'll talk more about those mesh description fields in the MPAS mesh structure lecture. So you can imagine that we might have run a simulation, and let's say that we were trying to capture the landfall of Hurricane Matthew, and we were to take one of our MPAS output files and to open it up with a program called NCView, which just allows you to visualize fields on regular one-dimensional, two-dimensional, or three-dimensional arrays. And if we were to take a look at the QView field, which is the water vapor mixing ratio field, we might see something that looks like this little screenshot here on the right. So it turns out that the left-right dimension here is the vertical dimension, and the bottom-top dimension that's being displayed is actually the collapsed horizontal dimension. And again, we don't know anything at this point about the ordering of the cells, so it would be rather difficult for us to make out, anything about the structure of Hurricane Matthew by looking at the native output in this way. So one of the primary tools that we use to interpolate model output onto a regular latitude-longitude grid is this tool called Convert MPAS. And this is just a simple Fortran tool that we've written and that you can obtain from a GitHub repository. And the URL is given here. But essentially, you clone the repository, and there's a README that will tell you how to compile it. It's usually just as simple as typing make, assuming you're using the GNU, Fortran, and C compilers. So in its simplest form, you can simply run the Convert MPAS tool on the command line with a single argument, and that argument is the name of an MPAS input or output file that contains all of the fields that you would like to interpolate onto a regular latitude-longitude grid. But you'll notice because we're only providing a single file to the Convert MPAS tool, it's necessary that that file contains not only the fields to be interpolated, but also the information about the MPAS mesh. If you happen to be working with diagnostic files, that's not the case. As we said earlier, the diagnostic files by default don't have mesh information. So in that case, you can provide multiple arguments to the Convert MPAS utility. So if more than one argument is given, then the first command line argument is assumed to be an MPAS file that contains mesh information, and the only fields that the Convert MPAS tool will read from that file are just the mesh description fields. No other fields from that file will be horizontally interpolated. And then all of the other command line arguments contain fields represented on the mesh described in the first command line argument, and which will be interpolated by the Convert MPAS utility. For example, if we had a whole batch of diagnostic files, we might say convert MPAS and the name of one of our grid files, and then diag_star.nc to match all of the diagnostic files in our run directory. And as we said, because the history files contain the three-dimensional mesh information as well, we could say that we wanted to interpolate all of the fields in all of our history files. But again, because we would be providing multiple command line arguments to the Convert MPAS tool, we would have to redundantly specify one of those history files, which would again only be used to read mesh information. The output from the Convert MPAS utility is always a netcdf file called lat-lon.nc, and although the program tries to be clever and to append records to existing lat-lon files, it's actually probably much safer if you just remove any existing lat-lon.nc file before you rerun the Convert MPAS utility. And by default, all of the output is interpolated to a 1/2 degree lat-lon grid, but this is something that you can change, as we'll see in just a couple of slides. So in our example simulation of Hurricane Matthew, after we've run the Convert MPAS tool and created this netcdf file called lat-lon.nc, we can open up that file using, for example, the NCView program, and we can change to the QV field and take a look. And looking here, we can see something that does actually look like a hurricane, and we can presume that this is probably the representation of Hurricane Matthew in our model simulation. But let's say that this was a fairly high-resolution simulation, and we'd like to see more detail about the structure of the hurricane in the interpolated fields. And you might find yourself getting your face closer and closer to the screen trying to look at the structure there. But a much easier thing is to just interpolate to a single region of interest at higher resolution using the Convert MPAS utility. So if we would like to interpolate our model output onto something other than a 1/2 degree latitude-longitude global grid, we can provide a text file in our run directory called target_domain. And inside of this file, there are 4 parameters that we can specify. So the first pair of these is the starting latitude and ending latitude of the domain over which we'd like to interpolate. The second of these is the starting longitude and ending longitude. So in other words, we're providing the latitude range and longitude range. And then we can lastly specify the number of latitude points that will be evenly distributed in this latitude range, as well as the number of longitude points that will be evenly distributed in this longitude range. And then after removing our lat-lon.nc file and rerunning the Convert MPAS utility, we then get interpolated output that is, in this case, on about a 1/10 degree mesh. So we've got 300 longitude points with a span of 30 degrees of longitude, and similarly for the latitude direction. And then opening this up with NC View, for example, we then get, in some sense, a zoomed in view of Hurricane Matthew. And of course, this is all interpolation, so we're not creating new information. We're presuming that our model mesh is high enough in resolution to match the high resolution latitude-longitude grid that we've specified here. It's also worth pointing out that you can provide another text file in your run directory called include fields, and this lists one field name per file, all of the fields that the Convert MPAS utility should interpolate. And this is handy if you only want to look at just 1 or 2 different fields from your history files. You don't want to waste time or disk space interpolating all of the fields. You can run the Convert MPAS utility in a much more efficient way by just processing a subset of the fields. So interpolating the output from the native unstructured MPAS mesh to a regular latitude-longitude grid and viewing it with, for example, the NC View tool is really nice because it allows you to get a quick look at some of the MPAS output fields and to browse around through the fields to get a sense of what's happening in your simulation. But if you intend to do any sort of quantitative post-processing, or if you'd like to produce publication quality graphics, you'll almost certainly want to work with the output on its native mesh. And to do that, many of us at NCAR historically have used something called NCL, which stands for the NCAR command language. And more recently, we're starting to switch over to do most of our work with Python. And in fact, if you look into NCL, you'll see that it's being put into maintenance mode. So although it's not going away anytime soon, the group at NCAR that has done most of the NCL development is transitioning to developing a new package for Python called Pingle. So if you go to the MPAS-Atmosphere download page, and towards the bottom of the page, you click on the link that says Visualization and Analysis Tools, that will take you to a page where you can download different examples of NCL scripts. And very soon, we'll post some examples of Python scripts that use Pingle as well. So on that download page, you'll find various examples of scripts. And the idea is that you can take those scripts and modify them to your own purpose. So for example, we might provide a script that makes a plot of the precipitable water field, but we expect that if you wanted to plot any other 2-dimensional field, you could easily go in and modify that script to select something other than precipitable water, or to create a horizontal slice of some 3-dimensional field, for example. So to that end, on that download page, what we provide is examples of various sorts of plots, again with the expectation that the exact field that's plotted in the example doesn't really matter because you can easily change that. So we have, for example, an example of a script that simply plots contours, either unfilled labeled contours or color-filled contours of a 2D or horizontal slice of a 3D field. We have an example of a script that actually draws every MPAS cell in the mesh as a color-filled polygon, filled with a color according to the value of whatever field is being drawn. We have an example of a script that allows you to specify 2 latitude and longitude endpoints, and then that script creates a vertical cross-section between those 2 points, and it actually shows a representation of topography in the model. So you can see if you look closely here, almost the terrain-following nature of the coordinate surfaces that are being plotted. And then we also have example of scripts that simply just plot different aspects of the mesh. So plotting the mesh on, for example, just a map background can be useful if you wanted to give, for example, a tutorial lecture. We also have examples of scripts that allow you to put some quantitative information directly in the cells that are being drawn. So a variant of the script that plots color-filled cells is a version that draws color-filled polygons for all of the cells. And it also draws outlines of the cells and then puts whatever value you would like inside of each cell. So here, I think we were looking at the lowest model level wind speed in meters per second. And this is nice, particularly if you're trying to debug a model failure. You can actually look at the numerical values of a given field, time step by time step, assuming you wrote out an output stream every model time step, and you can watch the numerical values change. And for example, you can look for large gradients in values that might lead to a model failure. So, post-processing and visualizing the model output on its native mesh required us to read and make use of some fields that describe the horizontal mesh. And now I'd like to convince you that we can really fully employ this mesh information to perform some sorts of operations in much more efficient ways. So as a motivating example, let's suppose that we'd like to find the model grid cell that contains a given latitude-longitude location. And if you've used other limited area models before, particularly ones that work on regular rectangular meshes that might be laid out on a map projection, finding the containing grid cell for a given latitude and longitude is a constant time operation. All we need to do is to employ the map projection equations, transform that latitude and longitude into an xy or ij coordinate in the projection space, and then that usually immediately maps to a grid cell or pixel coordinate in that model grid. Just by rounding the real value coordinates to the nearest integer. However, in MPAS, there is no map projection, even for limited area MPAS simulations. And as we said earlier in this talk, the horizontal grid cells in a mesh could in principle be given in any order. And so that means that in the worst possible case, what you would have to do is to compute the distance from your chosen latitude longitude to the center of every single cell in an MPAS mesh in order to find the MPAS mesh cell that was nearest, and by the Voronoi property, therefore contains that latitude-longitude location. So we could do that, and if we only needed to do this for one or two or a small number of latitude-longitude locations, maybe this naive approach would be fine. But if we need to do this many times, we'd like to do something a little bit more efficient. So, one possible way to make use of the mesh information might be to construct some sort of search tree or a data structure that allows us to perform efficient spatial searches. So that might be something like an octree or a k-dimensional tree or KD tree. And in general, with these sorts of data structures, there is some sort of setup cost to build the data structure. And often that looks like n log n, where in this case n would be the number of cells in the mesh. But thereafter, doing a spatial search in this data structure can be done in logarithmic time for a mesh with n cells. But there is an alternative way that makes more direct use of two of the mesh description fields, and that has no setup cost. So the idea is if we were to make use of the number of edges on cell array, which tells us for every cell how many edges or cell faces or neighbors that cell has, as well as a list of those cell neighbors given by the cells on cell array, we can find a clever way to navigate a path of monotonically decreasing distance from any starting cell in the mesh to the cell that contains our chosen latitude and longitude. And again, this can be done with no setup cost, and based on some intuitive arguments at least, the cost is about the square root of n per search. So square root of n is asymptotically a little bit worse than log n, but again, we don't have any setup cost. The neat thing about this too is that if we want to perform repeated searches for nearby latitude and longitude locations, the cost almost reduces to a constant time operation. So this method works as follows. So the idea is that we're going to start by just choosing any cell in the mesh, and that's described here in this figure by this blue cell. That's our chosen starting cell, but we could have chosen any other cell as our starting cell. And initially, we're going to set a what we call a test cell to an invalid value, to none, to null, to -1, whatever we want. And the idea is that we're going to continue to iterate while our test cell is not equal to our current supposed nearest cell. So in each iteration, we're going to set our test cell to our current nearest cell, and then we're going to probe around with this nearest cell. And so we're going to find out the distance from our test cell down to our latitude, longitude here, identified by this green dot. And then for every neighbor of that test cell, we're going to compute the distance from each neighbor to our latitude, longitude location. And anytime we find a neighbor of our current test cell that's closer than we are, we're going to set our nearest cell, our provisional nearest cell, to that neighbor. And then that's going to end the iteration. And at the beginning of the next iteration, our test cell is going to move to whatever neighbor among those of our previous test cell was nearest. So as iterations progress, you can see highlighted here this path. It's easiest to show here. If we take this cell, we can say that among all of its neighbors, this neighbor happens to be closer to our green dot here. So at the end of this loop here, our nearest cell is going to be set to this neighbor, and to this neighbor, and to this neighbor, and to this neighbor. And in the final iteration, we're going to search all of our neighbors and find that none of them are nearer to this latitude, longitude location than our test cell, and that terminates the algorithm. And I said that repeated searches of nearby locations are almost constant cost. The idea here is that if instead of a latitude longitude point here, we moved our latitude longitude point maybe a little bit to the west, what we do is we use our previous ending location as the start of our new search. And that means that we only have to search our immediate neighbors to find one that takes us to the cell that contains our new search location. Now, there's a similar problem to the problem of finding the cell center that's nearest to a given latitude longitude location, and that is the problem of scanning or processing all of the cells in the mesh that are within a specified radius of a given latitude longitude location. So in other words, we want to identify all of the cells in the mesh that fit inside a circle of a given radius. And again, we could do this in a naive way. So we could go for every cell in the mesh and compute its distance to the center of our circle. And if that distance is less than the radius of the circle, then the point is clearly inside the circle, otherwise it's not. Or of course, we could make use of some of the connectivity arrays or mesh description arrays to do this in a much more efficient way. So our algorithm works in the following way. Firstly, it makes use of a data structure called a queue, and a queue is just what's called a first in, first out data structure. So you can add elements to the queue, and when you pull elements out of the queue, they come out in the same order that they were inserted, just like the queue at a grocery store, for example. And as with the previous algorithm, this new algorithm is going to make use of this n edges on cell array and this cells on cell array. And again, you might recall that n edges on cell basically tells us for every cell in the mesh, how many edges or cell faces does that cell have, which is equivalent to the number of cell neighbors for any given cell. And the cells on cell array tells us what are the indices of the neighbors of a given cell in the mesh. So the first thing that we need to do in this algorithm is to find the cell that contains the center of our circle. And from the previous algorithm, we already know how to do that effectively. And we're going to assume that the cell that's at the center of our circle is within the circle. Otherwise, it means that the circle is less than the size of a single grid cell, in which case, the problem is trivially solved. So we're going to mark that center cell as visited, and we're going to insert it into our queue. And now comes the iteration. So while we still have cells in our queue, we're going to pull out the next item from the queue, the next cell, and we're going to call that C. And because we're going to maintain the invariant that a cell is only added to the queue if it lies within our circle, we know very first thing that the cell that we just pulled out of our queue is within the search radius. So now we can process it. So maybe we want to compute the average temperature in a circle of radius 500 kilometers or something like that. any sort of processing we want to do with all of these cells inside of our circle can be done at this point in the algorithm. And the next thing we're going to do is to scan over all of the neighbors of that cell that we just pulled out. And we're going to find each neighbor, and if we've not already marked that neighbor as having been considered by the algorithm, this means it's a new cell to us. We've never processed it before. And so we're going to firstly say, okay, we've considered it. But secondly, we're going to compute the distance from that cell center to the center of our circle. And if that cell is within the search radius, we're going to then add that cell into the queue. And so what we've drawn here in this figure is a color coding of all of the cells according to the order that they're processed by this algorithm. So you can see that this algorithm is what's effectively called a breadth-first search. So our search radius starts out and it slowly moves outwards, processing cells until we get out to the boundaries of the circle. And so these dotted cells represent cells that we considered right here, but were found to be outside of the radius of our circle. And so they weren't added to the queue, and therefore we never processed anything out further beyond them. So that's how the algorithm works. And the colored cells as well as the dotted cells represent all of the cells that were considered in any way by this algorithm. So you can see that it's fairly efficient in that we only consider the cells that are inside of our circle plus those cells that are immediately outside the circle, but nothing else. So to wrap up this talk, I'd like to point out one critical consideration when working with variable resolution MPAS meshes. And as a motivation for this consideration, let's suppose that we ran a variable resolution simulation that refined maybe from about 60 kilometer grid spacing over most of the globe down to about 15 kilometer grid spacing over North America, plus a bit of the Pacific and Atlantic Oceans. And let's say that we were interested in computing the daily precipitation rate, the global daily precipitation rate from our simulations. So we know that our diagnostic files contain grid scale and convective accumulated precipitation since the beginning of a model simulation. So we could say to ourselves, this is easy. All we need to do is to take each of our diagnostic files and to add up the two components of the accumulated precipitation, grid scale and convective. That gives us the total accumulated precipitation up to that day. And then we can just take two diagnostic files that are 1 day apart and to subtract the total precipitation in the earlier file from the total precipitation in the later file. And then we can just add up the values of precipitation for all of the cells, divide by the total number of cells in the mesh, and that would give us a globally average precipitation rate. And if we were to do that in our particular simulation, we'd find that we get a value of around 3.43 millimeters per day. And we might look at that and say, well, that seems a little bit high. But then we realize that we're working with a variable resolution mesh, and what we should be doing is taking an area-weighted average of the precipitation values in individual grid cells. And that turns out to be almost no more difficult than taking a simple average. So by the way, we've got an example here that happens to be an NCL, but I think if you're a Python user, you should be able to guess what all of this means. So what we're doing here is we're just opening up two diagnostic files on the 14th and 15th of October 2016. And from the second of those files, we're adding up the convective and grid scale components of the precipitation. And same thing for the first file, and then we're subtracting the first file value from the second file value. And now we need the areas of all of the grid cells, and that's something that's available either in the history output files or in the model initial conditions. So we can open up, for example, the initial conditions file, and from that, read the area of all grid cells. Then all we need to do is to take our difference and scale it by cell area, and then divide that total integrated value by what effectively is the surface area of the Earth in square meters. And doing that, we then come up with a value of the globally average precipitation rate of about 2.93 millimeters per day, which I think should be probably a lot closer to observed values. So the key point here is that when working with variable resolution MPAS meshes, but maybe as good practice when working with any MPAS mesh, because even for quasi-uniform meshes, there is some cell-to-cell variation in area, it's a good idea when taking any sort of horizontal integral or average to always make sure that you take into account the true cell areas. So for example, if you were working with a variable resolution mesh that refined by a factor of 4, that's a factor of 4 in the cell-to-cell grid distances, which actually means a factor of 16 in the cell areas. So it is critically important to take account of the areas of cells, particularly in variable resolution meshes. And on that point, we'll conclude this talk.